Hello students, in this video we'll do a simple example of computing a Jordan canonical form of a 3x3 matrix. Let's consider the matrix A, which is going to be 1, 0, 1, then negative 1, 1, 1 half, then 0, 0, 1. And let's compute the Jordan canonical form. So I'm making the illusion, so there should be this matrix A should have repeated eigenvalues. So let's check that's the case. So let's compute determinant of A minus lambda times the identity. And let's see what we're going to get over here. So if we do that and we set that equal to 0, we're going to have the determinant of 1 minus lambda, 0, 1, negative 1, 1 minus lambda, 1 half, and then 0, 0, 1 minus lambda. That's equal to 0. Now, of course, what we can see over here is if I expand along the top column, I'm going to have plus, minus, plus. So let's do the first entry over here. That's going to be a 1 minus lambda. And then this subdeterminant over here is going to be a 1 minus lambda quantity squared minus nothing. So that's going to be a 1 minus lambda squared. The 0 cofactor gives me nothing. And then this 1 entry over here, then what am I going to have? A plus 1, then negative 1 times 0, and then 0 times 1 minus lambda, so there's nothing there. So we exactly see that the characteristic polynomial is 1 minus lambda cubed is equal to 0. So lambda is equal to 1, and the multiplicity is equal to 3, right? So multiplicity 3, which means that we could have, if we're lucky, we could have a basis of eigenvectors corresponding to lambda equals 1, or we could have, so there's anything that can happen over here. So we can have a 3-dimensional basis of eigenvectors, we can have a 2-dimensional basis of eigenvectors for this, or a 1-dimensional. So let's see what happens over here. So let's find the eigenvector corresponding to lambda equals 1. So when lambda is equal to 1, let's look at the eigenvector equation. The eigenvector equation is going to be a what? It's going to be a 0, 0, 1, a negative 1, 0, 1 half, and then the 0, 0, 0 applied to V1, V2, V3 is equal to 0, 0, 0. Okay, so this is my eigenvector equation. And so let's see what will happen over here. So if we expand this out, we see that this implies that we have a V3, and then we have a negative V1 plus 1 half V3, negative V1 plus 1 half V3, and then nothing over here, 0, is equal to what? Is equal to 0, 0, 0. And so of course what this is going to tell me over here is this is going to tell me that V3 is equal to 0. This says that V3 is equal to 0. If V3 is equal to 0, that's going to force V1 to be equal to 0. And of course V2 is free in this case, so V2 I can choose to be 1. Okay? So here's my eigenvector. My eigenvector is 0, 1, 0. That's our eigenvector. And it's a 1-dimensional eigenvector space. So the eigenspace is 1-dimensional. Okay? So now I have to solve the generalized eigenvector equation, right? What's the generalized eigenvector equation? So that corresponds to a Jordan block. Now I need to find A of V2. We need A of W, for example. A of W to be equal to what? A of W has to be equal to what? Has to be equal to V. Has to be lambda W plus V. And this is my V over here. Let's call that V. Excellent. And so what does this mean? This means that A minus lambda, so A minus lambda, times identity of course, W is equal to V. This is my first generalized eigenvector equation. This is the generalized eigenvector equation. Okay, great. And so let's look at what that would entail. So what will my W vector need to satisfy? My W vector needs to satisfy the following. So I have what V is, right? And so now here's my matrix A minus lambda times identity, right, where lambda is equal to 1 in this case. 0, and then a 1, and then a negative 1, then a 0, then a 1 half, then a 0, then a 0, then a 0, applied to W1, W2, W3. Has to be equal to what? It has to be equal to V now. And my V is 0, 1, 0, 1, 0. Okay, good. And so what does this tell me now? This tells me that W3, over here, we're going to have that W3 is equal to 0, right? Good. And then what do we know about these things over here? So now what do my equations tell me? This tells me over here that the first equation tells me that W3 is equal to 0. And then negative W1 plus 1/2 W3, negative W1 plus 1/2 W3 is going to be equal to 1, right? And then finally, there's nothing over here from the last equation, right? So W3 is equal to 0, that's gone, and that tells me that W1 has to be negative 1, right? That's great. So now we found our W equation, our W vector is just going to be what? It's just going to be a negative 1, 0, 0. Perfect. And now that's this level of my chain of generalized eigenvectors stops at dimension 1, so I have to do one more step of this procedure. So now the next step of this procedure is the following. So finally, we need what? We need Q such that what? Such that AQ is equal to lambda Q plus W. Plus W. And so what will this look like as a matrix equation? As a matrix equation, this is going to tell me a 0, 0, 1, a negative 1, 0, 1/2, and then a 0, 0, 0 applied to Q1, Q2, Q3 has to be equal to W. And what's W? W is negative 1, 0, and then a 0. Great. Now what's that going to tell me? That's going to tell me over here that Q3 is negative 1, so Q3 has to be negative 1 from that top equation. Then negative Q1, and then plus 1/2 of Q3, 1/2 Q3 has to be equal to 0 over here. So that says that Q1 has to be 1/2 of Q3. So Q1 is going to be negative 1/2 because Q3 is equal to negative 1. So I just found my vector Q. My vector Q is going to be negative 1/2, 0, 0, 1. Great, so now I can write down the Jordan form of this matrix over here. So what's our Jordan canonical form? Our Jordan canonical form is going to be what? So our formula is going to be the following. So A is going to be the matrix that corresponds to the first the eigenvector. So the eigenvector goes in first. So the 0, 1, 0 goes in first. Then the first level of the generalized eigenvector, negative 1, 0, 0. And then finally the third level of the generalized eigenvector, that's a what? That's a negative 1/2, 0, negative 1. Then the Jordan block. So Jordan block is 1, 1, 0, 0, 1, 1, 0, 0, 1, like so. And then the inverse of this matrix over here. So 0, negative 1/2, negative 1/2, 1, 0, 0, 0, 0, negative 1, inverse. Okay? And that is our Jordan canonical form. Jordan canonical form. Which generally looks like A is equal to the matrix P, where P contains eigenvector, generalized eigenvector, generalized eigenvector, generalized eigenvector, generalized eigenvector, depending on how many generalized eigenvectors you have. Then the Jordan block, the only difference between the Jordan block and the actual diagonalization procedure is that you have 1s above the eigenvalues on the main diagonal. So that's on the super diagonal. On the super diagonal, you have 1s wherever there's the next level of the Jordan block. And that you put your Jordan block over here, and then your P inverse. So it mimics diagonalization, except with this kick that you have these 1s on the super diagonal instead of being a pure diagonal matrix. Thank you very much.